Okay, we're very pleased to welcome Heather again, who's going to talk about the Kauffman-Ogasa invariant.
Oh, okay. Um, so I'd like to thank you for coming to my talk today. So this is joint work with Liu and EG, and we've been working on this throughout the semester. So I know that most of you are familiar with this, but we'll just start with a brief review. So we've been looking at virtual link diagrams, and so a virtual link is a decorated immersion of n copies of the circle in the plane. So we'll have the two crossing types that you're all familiar with. And then one point of view that you can take is that virtual links are equivalence classes of diagrams determined by the Reidemeister moves and the virtual moves. So then we have our Reidemeister and virtual moves. And so you're all familiar with the first three moves. Those are the classical Reidemeister moves. And then we have our four virtual moves. So in the work that we've been doing, we've been considering the Kirby calculus and sort of a special version of the Kirby calculus as well. But we'll just start with our review of the Kirby calculus. So the Kirby calculus allows us to describe 3 and 4 manifolds using basically blackboard frame links, and the the uh, the moves that we're interested in here are the Reidemeister moves and the Kirby moves. So the Kirby moves allow us to introduce or remove a knot with a single crossing in it, either plus or minus. And basically in the Kirby calculus, these are equivalent. So we can introduce this. This is the same as introducing nothing, and this is the same as this introducing this Hoff link. And all these have in common is that they are S3. And S3 is a 3 manifold that we're looking at as a boundary of a 4 manifold. And then we also have handle slides, which we'll look at in a minute. But Kirby has his theorem that says, suppose the boundary of M sub L1 is equal to the boundary of M sub L2 for links L1 and L2, then L1 and L2 can be changed into L2 by the above moves. And so this is sort of, the centerpiece. So then we have handle slides, and here's some examples of handle slides. Right now I'm still focusing on the classical case. So here's an example of a classical handle slide, but then later on we're going to move into considering the virtual case. And when we think about the virtual case, our handle slide will also go through virtual crossings. And so when it's, you go over a virtual crossing, it'll just introduce another virtual crossing here. Okay. So then this brings us to the WRT invariant. And so the WRT invariant was actually one of the invariants that I studied when I was completing my thesis like 20 years ago. That has been a little bit of time. And so we're thinking about the Kauffman-Linz formulation of this, which uses the temporally Lieb recoupling theory. And so this is an invariant of 3 manifolds, and the way it is computed is basically by an in-depth understanding of the temporally Lieb algebra. And we take steep sums over all these different possible colorings of the knots. And in my original thesis work in the paper I co-authored with Liu, you can see a little link to it on arXiv here. we were able to formally compute this for virtual links. So we know that it also acted as an invariant of virtual links. And then in the original paper, we also looked at invariants under those two Kirby moves, the handle slide and the introduction or removal of the unknot with one crossing. So the interesting part there was actually looking at and doing the computation for the handle slide. And then at that point in time, when we were looking at it, this predated a lot of work on virtual links. This predated Cooperberg's paper about unique surfaces in which these virtual links were living in and all that work. So at this point in time, when we were looking at this, we had some speculations on like what would actually be a virtual 3 manifold and so on. The Kirby's proof of the Kirby calculus does involve the fact that you are actually working in S3 and that S3 is simply connected. And without that assumption of simple connectedness, there's questions about how do we push forward with this when now our knots are living in surfaces cross I, because that's another way of looking at virtual links. Since I recognize most of the people, I'm assuming that you're familiar with that alternate viewpoint that you can look at virtual links as knots and links embedded in surfaces cross I.
Yeah.
Correct me if I'm wrong, by the way, if anybody needs kind of a refresh there. So then Lou and EG this summer put out a paper, and this paper is here's the link here, entitled Quantum Invariance of Links and 3 Manifolds with Boundary Defined via Virtual Links. So they started looking at an invariant of 4 manifolds computed via virtual links, and sort of developed that and looked at a resolution to the issue of simple connectivity. So in reference to that, you might want to look at Justin Roberts' paper on arXiv, the Kirby calculus in manifolds with boundary. So in this paper, they have the 2 original Kirby moves, the handle slide and the introduction and removal of the unknot with one crossing. And Justin Roberts also introduced an additional move to deal with the fact that you are working in a surface cross I. So then, which one do I want to go to? All right. So in terms of kind of looking at that, and I move very, very slowly when I'm thinking about the Kirby calculus right now, we can think about our knot, or in this case, our link in a torus cross I. So there's our surface cross I. And if we view this configuration in S3, we get 2 unknots with 0 writhe. If you look at these curves as surgery instructions in the torus cross I, this produces a simply connected 4 manifold, sort of resolving that issue we mentioned earlier. But this also can be viewed as a virtual link. And this is the picture of the corresponding virtual link here. So we can there we go. So we can perform our Kirby calculus in simply, with curves with simply connected. So we can still perform our Kirby calculus in the surface cross I. And when we're working with surfaces cross I with links, properly inserted to resolve our simply connected issue, then that's also going to resolve the issue that they were worried about in the Kauffman-Ogasa paper. So here are two links in the torus cross-I, which are equivalent under the Kirby calculus. And then below each of these, I've produced their corresponding virtual link diagrams, which are also equivalent via the Kirby calculus, like the planner version of the Kirby calculus. So the Kirby calculus, when you start doing it in the torus, is a little tricksy because you can kind of push things off of each other because you've got these loops. So these two are equivalent via the Kirby calculus. It may not be the simplest thing to see though. All right, so that sort of sets the stage for where Lou and Iji were at when they started talking to me about this project. So in my original thesis, we did some calculations about the WRT invariant, and to move forward with the work in their paper, they wanted to do some very specific calculations of their modified invariant. So we'll now start talking about the calculation of the invariant. So to begin this part of the story, what we need to look at is the temporally Lieb algebra. So this is an algebra of elementary tangles over z tilde a inverse. The z tilde part just indicates that we're looking at basically rational functions. So in the two-strand temporally Lieb algebra, we have two generators here. We have I and U1, and then here are the generators for the three-strand temporally Lieb algebra. So similar to the like braid formulation of the braid group, similar to the braid group, we have some relations on our generators, namely that ui squared is d times ui. We have, I think of this as kind of being like an R3 move type relation. And this one allows us to kind of swap the position of ui and uj if they're sufficiently far enough away in the braid. So here's just kind of a sample multiplication to look at. When you multiply two U1s in this case, you get a circle in the middle, and this becomes D times the generator U1. And here we're taking our D to have this value. So I'm making a very short story about the temporally Lieb algebra here. There's quite a bit more work published. So once you've had that set up, we then go on to basically the Q symmetrizer. And the Q symmetrizer plays a very key role in the reason that we're able to actually compute these type of invariants for classical links. So we're actually looking, so we start with the temporally Lieb algebra elements, and then we are actually computing a trace here. There's a recursive definition that you can give for the symmetrizer, and this is actually the one I usually start with. I think I might have a typo here. But I'll worry about that. But this relationship is the important one because it allows you to effectively unspool the symmetrizer and drop down so that you're looking at essentially lower in lower number of strands. And then this symmetrizer also has two important properties. One is that if you attach a UI to multiply the symmetrizer by UI, you get a 0. That's the turn back. And then it is also in idempotent. So once we have this set up, we can start assembling larger and larger components, right? So we can look at what we refer to as a 3-vertex, and this is effectively an element in our temporally Lieb algebra. So we have A strands coming in over here, B strands coming in, and then C strands coming in over here. And then the relation, because there's like a flow going from this side to the C side to the B side, and that is that I, J, and K have to satisfy these relationships. So up to this point, I've been kind of thinking about these things abstractly, and we had the evaluation we saw earlier when we took the closure that a single loop was going to be D, and D is the negative A squared minus A to the negative 2 that we are used to using from the bracket polynomial. So to compute our invariant, though, we'd actually like to have numerical values. So then we get into taking our A to be a particular value of I'm just going to say a particular value. So we let our A equal E to the I pi over 2R, where R is the number that we select and fix. Because if you take powers of this, eventually you cycle back around to 0, we get some admissibility conditions, right? So in particular, in order to get non-zero values, you have to have A plus B plus C is less than or equal to R minus 4, where A is taking on a value which is less than or equal to R minus 2. And all these combinations here have to be non-negative. So this will allow us, if we have this setup going on, to actually compute a complex number as a value of our invariant. Okay, questions? So Lou talked about some of these relationships a little bit.
Sorry, Heather, but sorry, what was A again? Capital A?
A is E to the I pi
yeah, I
over
can see
2R.
that, but how does it come in? I mean,
so
it's the bracket polynomial variable.
Yeah.
Oh, of course. Okay, sorry. Yeah.
And I guess you could use any 2rth root of unity. You don't have to use that one.
Yeah, but this is one, that's usually used in this particular formulation. And it's set up so that you can define the admissibility conditions. So you can think about this entirely abstractly, just as algebraic elements without specializing your A, and not really worry about specializing your A till later. Because you could expand this entirely without having that evaluation. You would just wind up with some big polynomial. But so sort of the key features is we have this 3-vertex setup. We can convert the 3-vertex to an element of the temporally Lieb algebra in the using our Q symmetrizer. And so basically when you expand all the Q symmetrizers, you wind up with a big pile of crossingless loops in the plane. So each crossingless loop will have the value D, which is negative A squared minus A to the negative 2. And then you would just evaluate that overall to get the particular value, right? So in terms of the Q symmetrizers and the loops, we have formula set up already that recur a lot. And so the formula that we see a lot is we get something called a theta nut. And we'll kind of see how that rolls out in a second. And so this is denoted theta, A, B, and C. Our order does not matter. There is a tetrahedral net. And then here's kind of the link that we would see between the knot or link diagrams and the and our temporally leave algebra. So if you look at this and you realize and you let A equal 1 and B equal 1, the expansion here with the Q symmetrizers basically just turns into the usual expansion, the one we get with the bracket polynomial. You would have like a vertical expansion, and then you would have that horizontal expansion. So that would be the conversion here. But now we're letting our A and B, so you can think about them as like coloring it with like n strands. You get a more complicated expansion. So we'll use this relationship to convert each link to a trivalent graph. So I have kind of an example of how that process works. So let us take a look at that. So here's kind of a classical example. This is actually originally done in what was the name of the book? The temporally recoupling theory book. And when we started doing these computations, I used this as sort of like a trial case to make sure I was programming everything correctly. So you start with your knot diagram, and I have it labeled W just to indicate that we are going to compute our invariant. So it's like W bracket. And so then what we do is we are summing over all possible colorings of the particular diagram. And the coloring is given by A. So if you've selected your R value for our large A variable, this will basically run from 0 to R minus 2. So you have the sum of the different colorings, and then you can apply the expansion that we saw in the last slide, where you convert each knot crossing into a pair of trivalent vertices with these additional relations. Then there is also a relation that allows us to convert a horizontal bar into a vertical bar. This is related to the handle slide proof that Liu showed in his talk. And you get a big pile of formulae. Probably the important thing to focus on is this trivalent graph though. And what happens is that there is a relationship basically that allows us to remove successively the bigons in the trivalent graph. And so as you remove the bigons, your trivalent graph gets simpler and simpler as you move along until eventually at the end, you just wind up with this summand down here. And for the summand, you just basically figure out which cases are admissible. And that can get a little complicated. And then you sum over all possible cases. So I think for this case that we're looking at here, if you look at just take R equal to 4, the problem is there's like 243 possible cases you have to consider. That's, and then we have a normalization. So to do the normalization, you set up your linking matrix, you compute the eigenvalues of the linking matrix, which are invariant under choice of orientation for the different possible orientations in a link. And then you have the number of components C. And this is basically set up so that the invariant applied to S2 cross S1, which is the a knot with no crossings, is equal to 1. So, right. So in terms of actually computing that, we do use Mathematica. So we can explicitly, let me kind of try to make this a little bigger. Right. So we can explicitly program in the values for each of these things. Del is like delta n. And so we have actual formulas for all of those tetrahedral functions that I was talking about and the theta functions that I was talking about. And then basically you set up the sum end. And I should be able to page through this. And then once you've done that, you basically just evaluate which of the potential sum ends are admissible and add them all up. So I'm kind of simplifying things a little bit here for the, right? So to give you an idea here, I computed which of the 243 cases were actually admissible. So kind of here's an example of what each of these individual terms will look like, and then you go from there. Right. So that's kind of a snapshot. Now, although this is the method of computation we're using here, you may be aware of Liu's and Sostenes-Lin's book on the temporally Lieb algebra, and they did do a huge number of the classical knots and links in that for the classical WRT invariant. They did not use this method, I believe. They used a different method, which I'll talk about towards the end of the talk. For various reasons, that method is just kind of not available. So here's kind of a summary of what I just went over. This was our computation for the positive trefoil. I picked a fairly small R value. There are 243 cases we have to evaluate. In the original colorings of the trefoil, we start off with A, runs between 0 and 2. As you're doing the transformation into a trivalent graph that we can actually compute with, you pick up some other variables and go from there. So for the classical case, you know, kind of our procedure is as follows. We just convert our diagram to a trivalent graph. We use this exchange relationship here. Cij is kind of a stand-in for a coefficient I did not want to fully write out. And what happens is if you have a face of this diagram that is bounded by, like, you know, 5 edges, 4 edges, you can use this exchange move here to sort of compress it down to a bigone. So you just compress your regions to bigones, and then there's a formula for removing a bigone. And since you're simplifying down the diagram, eventually you're going to get to a state where you just have a single circle, which is colored by A. So the alternative approach that was utilized in Lin's and Kauffman's book is called the shadow world, and I will touch on that briefly at the end. So now we can talk about the virtual case, which is what we are interested in for doing the computations in Kauffman and Ogasa's paper. And the first thing we can see is there are some problems. So here is the virtual Hoff link, which is basically one of the simplest virtual links that there is. And so we start to do our procedure. We take our crossing, we convert it. So now I have a trivalent graph, but this is a non-planar trivalent graph. And essentially we get something that looks kind of like a theta, but it is a non-planar theta because these vertices are rigid. So this is what I'll call a twisted theta. And in our twisted theta, the order doesn't matter. We can just take this one edge and move it with our Reidemeister moves over to the other side. So the order of A, B, and C doesn't matter, just as it didn't matter in the classical case. Now, if we take one of these strands to be 0, basically saying there's no strands going through that, the twisted theta in this case would resolve to a delta A. So basically an unknot with A strands and a Q symmetrizer placed on it. But more importantly, we're no longer in our temporally Lieb algebra. So once we've gone over to the virtual case, we've actually moved into the Brouwer algebra. So our Brouwer algebra acquires some extra generators. So we have our elementary tangles that we saw before, but now we have 2 cross strands. Here would be the generators of the 3-strand Brouwer algebra. And there's some additional relationships. Hang on, I need to, my kids are in school, and if my phone goes off, I just need to check and make sure. They apparently only call you once. All right, anyway, so here we have the additional relationships on the Brouwer algebra, and then we have some mixed relationships as well. So these have sort of, or at least I consider them to have a relationship with the Hecke algebras and the Berman-Wenzel algebras. So Berman, Wenzel, Murakami algebras. And I know Sophia and Hugh have done some work on those, and they've done some work where they've produced invariants of knots and links. The big problem here is we don't really know what happens to the Q symmetrizer when we move to the Brouwer algebra. So let's look at the next picture. So here we're back looking at our trivalent vertices, and now suddenly these strands coming from our trivalent vertices can cross. So this would create the twisted theta that we saw earlier. And for simple twisted theta, where we have low strand numbers in here, we can fully evaluate this by hand. So here's our trivalent graph. Here's the conversion to the Q-symmetrized picture. And these Q-symmetrizers, because of the idempotence, just get absorbed. And we're basically left with this picture here, which is the 2-strand symmetrizer. And so then we just take the identity here, and then we have this subtraction of delta 0 over delta 1, and we're left with this. And then we get an evaluation here. So we have some evaluations that we did by hand to accomplish the computations we were interested in. So I didn't fully put in all the computations here because it looks very similar to an expansion of the bracket polynomial. But essentially our problem is that our trivalent graphs are no longer planar. The shadow world actually makes use of regions in the plane, and our regions may not be well defined anymore. So here is the planar tet net that we saw originally and was a part of our reduction formulas that we used. But now once we allow these crossings, there are some other forms of the tetrahedral net that we'll see. So we would see this one here where this is a virtual crossing. We might see this one here. And I suspect there are some other possible reductions, not reductions, but some modifications of the tetrahedral. So these still have the tetrahedral shape, but now our relations that from the temporally Lieb algebra are no longer going to apply when we try to reduce because of the crossings. So these types of reduced elements actually do appear in the diagrams that we'll see. So this is one of the elements in the diagrams that occurred as I did the reductions. So if you'll look at this, you'll realize that I need bigons to do the reduction. And no matter which, so I could take this strand here and convert it to a vertical strand, but I'm not going to get a structure that will allow me to produce a bigon and then remove a bigon and keep doing that procedure to reduce. So I no longer have that ability to do the compression and reduce down to the unknot. So this brings us just to some questions about the algebra, separate from the problems about the four manifolds. It would be nice to have a formula for the evaluation of all the twisted theta for any values of A and B and C. This is sort of more of a graphical problem when you're looking at these rigid vertices. What are all the possible twisted tetrahedrons that we could come up with? And then we would need an evaluation formula for the tetrahedrons. And then even just moving back to the Brouwer algebra, taking the symmetrizer and attaching one of those, just a single crossing, how does that evaluate? Having a consistent formula to that. And then it's clear that I don't think, unless we come up with some new formulas, we would always be able to simplify down to the bigons, the twisted thetas, and the tetrahedrons, right? That was a key part of how we were reducing to get the invariant. All right, so here is kind of a sample computation. This is one of the virtual links that we were looking at for the purposes of comparing the invariants. And here is sort of how the computation rolls out in this case. So we have our linking matrix. And from the linking matrix, we can compute the terms needed for the normalization. You can see that this has 4 components. So right away, we have 4 labels that we have to consider. And this is the symmetrize. So basically every time you see a D or an A, there's a symmetrizer associated with that. So this is sort of the unnormalized invariant. And then we expand and keep expanding and reducing until down here we get to the only remaining thing is a twisted theta, which we have a formula for in the cases I was looking at. And then we have to consider these admissibility conditions. All right, so we've done quite a few of these computations. And so this is sort of a summary of where our computations are currently at. So the knots that we selected to compute were carefully selected to show that they actually either differ or agree, because there's some calibration computations in here. And so our current computational results support the theorems in Liu and E.G.'s paper that these are actually different and differentiating the things they wanted it to differentiate. So, however, we don't really have a strategy for computing these invariants in bulk. So now I guess I'll flip over and spend a minute discussing the shadow world, which is really where we need to be to compute these invariants in bulk. So the shadow world was what they used to do the bulk computations in the original book. And instead of going to trivalent graphs, they use the planarity of the diagram. So since it's a planar diagram, if you have a crossing, each crossing meets up at different regions. So it's possible to label each vertex, each edge, and each region. Then to this configuration, you can associate a particular evaluation. So these values combined, they gave it the name as tetnet. And then basically what happens is you can look at all possible coloring choices of the diagram. So coloring choices of A prime, B prime, and B, these for your vertices, edges, and regions. And then what you would do is you would take a product of each over each vertex, edge, and region or face in the diagram, right? So then you're sidestepping the reduction procedure that needs to be done by hand. But our virtual knots are living in the surfaces of, higher genus surfaces like the torus or higher. So then we start to run into a problem with defining the regions. So we have regions. It's just they don't lay out as nicely as they do in the planar case. And you start having to worry about sort of the twisting of the diagram in terms of how are we defining these regions as it goes along. So to effectively do the shadow world computation, we'd have to stay with the diagrams in the torus so we could determine what regions are what regions, if that makes any sense. Which of course loses some of the convenience of the diagrams. All right. So I guess this is basically where we are with the calculations in our talk. And I'm happy to say that the calculations support E.G.'s and Liu's theorem that they're actually differentiating these things. So I would like to thank you for hearing my talk.
Oh, thank you very much, Heather. Are there any questions?
It's interesting how in the original case, the translation to the shadow world depends so heavily on the plane. You start with a line in the plane and just move it across the diagram until it all gets translated. But that translation procedure isn't going to go over to things on surfaces. So maybe there's an ultimate generalization of the whole thing that would work.
Lou, there's a paper of Joanna and mine called Shadow World Evaluation of the Yang-Mills Measure that does exactly your shadow world on surfaces.
Oh, great. That's great. What is the reference for your paper?
It's in AGT, and it's just called Shadow World Evaluation of the Yang-Mills Measure.
It's in the archive.
It's in the
AG.
archive. It's on AGT. Just algebraic and geometric topology, their website.
Okay.
Okay.
Great. We'll look at it.
I have another comment to make. And, the volume conjecture has progressed to the point where they're doing it with Reshetikhin and Turayev invariant, the Reshetikhin-Witten Turayev invariant.
Certainly.
And the trick is to not use the root of unity you're using, but rather use a root of unity that breaks positivity. So what happens is that root of unity, it was chosen so there was positivity in the theory, and the positivity in theory causes the invariants to grow polynomially. But all you do is you just choose that root of unity in a different range, and they grow exponentially. And then the exponential growth rate has to do with the hyperbolic volume.
Do you have a paper reference, Charlie, for that?
You know Tian Yang, the name Tian Yang, Tianyang. He's the guy that's really pursued this. But the original idea
Would you spell his name again?
Tianyang. He's a professor at Texas A&M. He writes papers with Effie sometimes and with Francis. Okay, but the original idea from all this comes from Francois Costantino, who figured out that the evaluations of these theta curves and tetrahedra grew exponentially when you chose the root of unity in the right range. And so if you look at earlier papers of Francois, you'll find this happening.
So, Charlie,
I found his paper. That's easy to find on the archive. Good.
Go ahead.
So he was actually looking at the theta nets and things like that, because a lot of the time when I try to look up stuff on the Brouwer algebra, they're not concerned with these types of calculations at all. I mean, their interest is very we want to show certain things about the generators and So when
this goes back, this was about 2004. He was doing this. That Francois, that is, and then the stuff with Tian Yang is absolutely recent. It's only on the archive, and he's doing it with a graduate student. And then he has an earlier paper he did with Chi Chen where he did it with what he called the Turayev-Viro invariant, which was actually the sum that Joanna and I used in our quantum content of the normal surfaces paper from JKTR. And then he's got, there's lots of stuff. So it was a great talk, Heather. I enjoyed it a great deal. Thank you.
I feel like I know Lou's and EG's talks were quite topological, but then when you suddenly get into computing the invariant, it's very algebraic. It's very different. I feel like I have to turn on different parts of my brain when we have conversations about it. I have to switch back to thinking about the topological side versus the algebraic side. So, but thank you.
Well, thank you again, Heather. And if there are no more questions, I think we've all got to go into this shadow world and see what we can find.
Bunch. Who's next week?
Oh, next week it is. I'm not sure. Is it Sam? Yeah, I think it's Sam next week.
Okay.
I'll find out. Yeah.
Mm-hmm.
But anyway, I'll send around a note about it. So
That's great.
well, okay. If there are no more questions, I'll stop recording and hope to see you all next week.
Thank you, Roger.
Okay. Bye now.
So we're meeting in an hour, right?
Yes, we are.
Good. Okay.